Okay, so we're going to look at the relativistic multiplier, and we want to do that by looking at the distances that the light travels for the observer, and the observer sees it like this, and for the person who is actually running the experiment on the ship, and they see it like this. Now, the time it takes for the light to get from here to here is going to be the same amount of time that it takes the ship to get from here to here. The x components of the velocities are the same. So let's draw in our vector for the ship. And there we have it. So this here represents the distance that the light travels according to the observer on Earth. And we know that velocity is equal to distance over time. And that means that distance is equal to velocity times time. So if we're looking at the distance the speed of light travels, we know that the speed of light travels for the observer at a speed c and a time t. That t is the time as it passes on Earth for the observer. And here is the speed of light times the time as it's seen by the observer on the ship. So this t naught is the time in the inertial reference frame. And this here is the velocity of the ship times the time as seen by the observer on Earth. And here's our triangle. So we'll notice along the hypotenuse we have the distance that the light pulse travels as seen by the observer on Earth. Our far leg is the distance that the light pulse travels as seen by the observer in this ship. And right along the bottom is the distance that the ship travels as seen by the observer on the Earth. Now you'll note that we're using the symbol t to represent the time as the Earth observer experiences it, and we're using the symbol t naught to represent the time as the traveler experiences it. So let's take a closer look at our triangle. We know that it's a right angle triangle, and so we can use Pythagoras' theorem here to solve it, or to look at the relationships. So here we have the distance the pulse travels as seen by the observer on Earth. Here we have the distance the ship travels as seen by the observer on Earth. And here we have the distance that the pulse travels as seen by the observer on the ship. So we continue on and we square each term. So we're distributing that squared term throughout the brackets, and we have c squared times t squared equals v squared times t squared plus c squared times t naught squared. What we're trying to do here is relate the time as experienced by the Earth observer to the time as experienced by the space traveler. So we want to get t onto one side of the equation and t naught onto the other, and we can see here we have t and t naught on the same side. So we want to move this t over to the other side, and we'll do that by subtracting the term v squared times t squared, which leaves us with this expression here. We can see t naught, the time is experienced by the traveler, is related to t, the time experienced by the Earth observer. But we want to solve for t squared, and so we'll see here, we can see here that t squared is in both of these terms, and so we're going to factor that out. And now we want to isolate t squared, so we need to get rid of this term here by dividing both sides, leaving us with this expression here. Now, we want t related to t naught, and we have t squared related to t naught squared. And so we're going to square root both sides, and we're left with this expression here. Now we're very close to the expression that Einstein came up with, but it's still not quite simple enough. So we're going to do a little bit of an algebra trick, and we're going to multiply this term v squared by a factor of 1. Now remember that a number divided by itself will always be equal to 1. So in this case, we're going to use the number c squared over c squared. So this here is equal to 1 because anything divided by itself is 1. So it looks a bit more complicated, but we're still working at simplifying it, and you'll see that now c squared is in both of these terms, and we can factor it out. So here we factored it out, and now we're going to take the square root of both of these. We're just going to split that radicand sign and take the square root of c squared, which is c. And now we have this c in the numerator, a c in the denominator. They will cancel each other out, and we now have an expression for time dilation. This expression tells us how time on Earth is related to time in the spaceship. And this term here, 1 minus v squared over c squared, is called the relativistic multiplier. And we're going to be seeing this term a fair bit as we move through this unit.